So again, you should have gotten to 2.8, and we'll go from there. So to give you an idea of what we're going to cover, all right, we've got lesson 2.8, and we've got 2 quizzes there. All right, adding and subtracting complex numbers, and then multiplying and dividing complex numbers. All right, so we'll look at 2.8 here. 2.9, we can gloss over it quickly just to show you what the performance task would look like, but we're not doing this project, okay? Don't even attempt to do the project. It's very, very lengthy here, all right? This is something that if we were in actual class, this would be something like a big project, or maybe even like a STEM project type thing. Okay, so we're gonna gloss over 2.9 quickly, but there's nothing you have to do in terms of extra credit or quizzes for 2.9. All right, and then obviously 2.10, there's a checkup, there's a review, and then there's your CST. Okay, again, you only have to do the CST and not the TST. All right, so that's what we're going to cover today. All right. I mean, I'll pause here for a second, but I usually expect nothing. Anyone have any questions at this moment? Okay, awesome. So if we look here, we're reviewing complex numbers. All right, so we're going to review complex numbers. All right, and we did talk about this a little bit, I believe, in semester 1 of algebra 2. Okay, so it's this thing called complex numbers. All right, and technically all numbers are complex numbers. They're just not always written in this form that we're going to be more familiar with in terms of complex numbers. Okay, and it says, why are we studying complex numbers now? Because we've been dealing a lot with radicals and taking the roots of things and what that means, right? And I kind of hinted at it earlier on here, but the reason that is because if you look here, this square root of -5, all right, square root of -5, all right, we've been talking a lot about, okay, great, I don't know how to do that. Well, now we're going to learn how to actually look at the square root of negative numbers, and obviously not only that, but how we can add, subtract, multiply, and divide with them. Okay, so we're going to look a lot at this thing called complex numbers, and how do we take square roots of negative values here. All right, so if we get on into it here, earlier in the course, we learned about imaginary numbers, okay? And if I click on the definition for imaginary numbers, just to remind us here, there are numbers where the square roots are negative numbers, okay? So where the square roots are negative numbers, all right? And then the imaginary number I is defined to be the square root of -1. So if we look here at this example they gave us, if I have the negative 25 and I take the square root of it, it's like saying the square root of 25 multiplied by the square root of -1. All right, those two multiplied together. Okay, and obviously the first one here, the square root of 25 gives us 5, and we have this definition now that the square root of -1 gives us this value of I, right? So this is going to be 5I, right? It's going to be 5I. All right, so again, in other words, this imaginary unit I is the square root of -1. Okay, the square root of -1 here. All right, and what we can do is we can rewrite the square root of any negative number by using this new fact here. So if I have the square root of -a, this is like saying I square root of a, all right? Because again, I stands for the square root of -1. So the steps for doing this here, factor out -1 from the radicand. We split the radical in 2, and then we replace the -1 with I, or the square root of -1 with I. All right, so first, if we look here, factor out the -1. All right, so you've got -1 times by 7. And as we know here, we can split these into 2 as long as we keep multiplying them. All right, so great, we can do that. And now we can simplify the square root of -1 to I. So we've got I times the square root of 7, or we get rid of that multiplication symbol and we're left with I square root of 7. Okay, same thing here. Factor out the -1, split up the radical, simplify down to I multiplied by square root of 11. All right, and then obviously we get rid of that multiplication symbol. All right, so hopefully nothing too terribly difficult here. All right, and then if we look at two more examples here where the radicand is a perfect square, right? It can also be simplified. So we already looked at this negative 25 here, but those are the steps. All right, so we split it up, we take out the negative sign. All right, we split up the radicals. All right, square root of -1 gives me I, square root of 25 gives me 5, so I'm left with I times 5, or we write it number first, so it's 5I. All right, same thing over here. Factor out the -1. All right, split up the radicals. Then we simplify. So square root of -1 goes to I. 196. If you take the square root of it, that gives you 14. So you're left with 14I here. All right, you're left with 14I here. All right. So hopefully, again, hopefully it's starting to jog your memory here a little bit. Okay. Now. Sometimes expressions can have, again, both imaginary units and complex numbers. All right, they can have both imaginary units, imaginary units and real numbers, and this is what we call our complex number, right? We call our complex number this entire thing here. All right, so it's got the real part and it's got the imaginary part. Again, imaginary being the I, right? So real, imaginary, real, imaginary. Okay, so complex numbers are usually in this form A, and it should say plus or minus, right? So it's A plus or minus BI, all right, where A and B are both real numbers, all right, and I is our imaginary unit, okay? I is our imaginary unit. So if we look here, real part is 2, the imaginary part is 3I. Real part -1, imaginary part I. Real part 5. Okay, hopefully we're picking up a trend here. The first part is the real part. The imaginary part is the part with I in it. Real part square root of 3. Imaginary part is I square root of 5. All right, and again, don't let the radical make you think that it's not real. Okay, it's still real as long as it's a positive value. All right. When we start to get into, obviously, negatives under the radical symbol, okay, if they have that index value that's even, right, so square root, cube root, or I'm sorry, square root, root of 4, okay, root 6. If it's even and it's negative, that's what turns it into this imaginary part here, okay, imaginary part here. All right, and now a good thing to notice here, real numbers can be written in the form A plus BI, where B is equal to 0, okay? And imaginary numbers can also be written in the form A plus BI, where A is equal to 0, right? So earlier, when we looked at those top values, okay, it could have been just the value 25, right? So 25 would have been our A value, and it's saying we can have basically 25 plus 0I, right? We can have 25 plus 0I. Or if I just have this imaginary part, right, I square root of 5, okay, if I just have this part, right, if this real part here is 0, okay, if this real part here is 0, technically it's still a complex number, right? It's still a complex number. All right, so that means that complex numbers include all real numbers, all imaginary numbers, and then obviously the things that we're more familiar with, this A plus BI form, okay? Everything is technically a complex number. All right, so with that being said, since everything is a complex number, we can think about it as that way, right? We can think about it in that form, so we can add or subtract these complex numbers. Okay, we can add or subtract these complex numbers. All right, so what we're gonna have to do is we're gonna have to look at things in the form of like terms. Okay, in the form of like terms. So when we're talking about like terms with complex numbers, we're talking about the real parts and the imaginary parts. Okay, so the two steps for adding this together here, collecting like terms and then simplifying. So if we collect the like terms here, we collect the real parts first, we collect the imaginary parts second, or, you know, in the same step, all right, and then we simplify. Okay, so we just do our basic addition or subtraction the way that we see it, right? We do our basic addition or subtraction the way that we see it, okay? And obviously, again, this is 3i and this is just normal I, okay? So those are like terms, and then 4 and 1 are like terms, okay? So collecting the real parts, correcting the imaginary parts, seeing if they're like terms, and then obviously adding or subtracting using our notations here, okay? If we're going to subtract, okay, if we're going to subtract, right, per usual, okay, it's always important to keep track of our negative signs, okay? It's always important to keep track of our negative signs, all right? So first here, we're going to distribute the minus sign over each term. Then we're going to follow the same steps, collect like terms, and then simplify. So again, distributing those negative signs first. Okay, so this is going to turn into positive because this becomes negative. And then negative and negative makes it a positive. All right, same thing here. Negative and negative makes it a positive, and then I've got a negative positive. All right, so again, just distributing that negative sign, all right, multiplying everything by -1. All right, so then once we have distributed that negative sign here, okay, we're going to collect our like terms, so our real parts and our imaginary parts. All right, so we collect all of those first real numbers. Now we collect all of the imaginary numbers. All right, again, obviously bringing the signs that they have with them. Okay, so we've got 7 minus 2 plus 3, right, plus -3i plus 2i minus I. Right, again, being really careful with your signs here. All right, and then from there, it's just basic addition or subtraction. So we can simplify this down, and we end up with 8 minus 2i. Okay, end up with 8 minus 2i. All right, again, you're going to notice the key there is always going to be making sure we're collecting our like terms. Okay, making sure we're collecting like terms and keeping track of our signs here. Okay. So we can rewrite, or sorry, just to confirm here, all right, so we've learned about imaginary numbers and complex numbers, all right, so we've learned about imaginary and complex numbers, and we looked at very briefly how to add or subtract complex numbers here, all right. So again, if we have any negative number underneath a square root sign, we can rewrite it using an imaginary unit. All right, and that imaginary unit is the letter I, right? So again, the square root of -1 gives us a value of I. Okay, I stands for, of course, our imaginary unit there. All right. Ooh, sorry, hiccups. Okay, so then what is a complex number? How does it relate to an imaginary unit? Okay, of course, our complex number is in that form a plus or minus bi. Again, a and b are real numbers. And how it relates to the imaginary unit is, of course, that second number has the real number and the imaginary unit of I for the square root of -1. All right, how do we add or subtract our complex numbers? Okay, basically, if there's a negative sign, you got to distribute those signs so we keep track of the appropriate operations. Okay, and then in both of them, you're going to collect the like terms and then simplify. Okay, so again, not anything terribly difficult, I hope. Okay, so if we look here at a couple practice problems, all right, I've got the negative 121 here. Right, -121 here. So if I split this up, right, the first step is to factor out a -1 term. All right, so I would have underneath my radical symbol here, I'm going to have -1 times by 121. All right, then we can split that into 2 radical symbols. Right, we can split that into 2 radical symbols. So we know that the square root of -1 is going to give us this value of I. Right, so we have this value of I. All right, and normally what it would look like is it would look like that first answer there. Okay, we are going to look something like this one, I square root of 121 here. All right, except for we know that it can be simplified down even further. Right, it can be simplified down even further because the square root of 121 is 11. All right, so our answers for this are going to be letter A and letter D. Okay, because they're the same thing. It says what expressions are equivalent. All right, so letter A and letter D. All right, Looking at this here, right? And I'll just do this last one and then I'll leave the other two for you. Okay, remember, looking at this guy here, we've got to collect like terms. So first off, the two like terms I'm dealing with are 3 and 7. All right, so I'm going to have 3 plus 7. So that's going to give me 10. All right, so I'm dealing with either letter A or letter D. Okay, so that real part there gives me 10. Then I've got 7i minus 9i. Right, so I'm going to have a minus 2i. All right, so that's going to be my answer here. All right, obviously 3 and 4 are more practice problems, and I'll leave those for you guys so that you can try them out. All right, moving forward to this check your understanding here. All right, this one's a really, really good problem here, so I don't want to spoil the answer for you, but obviously there are multiple right answers here. Okay, so taking it through each step by step. Okay, taking it through step by step in order to find all of the correct answers, right? When I mean step by step, I mean split out the -1, right? Simplify down just that -1 value. Then seeing, can I simplify down 81, right? What would that give you? All right, so yes, there are multiple answers here. All right, again, dealing with the sum or the difference. All right, the first thing would be distributing any negative signs if necessary. So obviously we would distribute the negative signs down here for number 3. All right, then for 2 and 3, you're gonna again collect the like terms. So collect your real parts, correct your imaginary parts. All right, and then obviously you know how to do basic mathematical operations from there. All right, and then obviously 4 puts together subtraction and multiplication. So again, subtraction and addition. All right, so with this one here, obviously distribute that negative sign first, and since there's no other negative signs to distribute, okay, once you've done this second term here and you distribute that -1 to both, you can again collect like terms and do the operations as you see them. Okay, all right. Okay, so now we obviously remember what complex numbers are. We know how to add and subtract them. All right, now we can look at one more step up here, multiplying and dividing them. All right, multiplying and dividing them. All right, and again, multiplication with complex numbers is a lot like multiplication with polynomials. All right, again, we just think of our imaginary unit I as a variable. All right, we think of it as a variable. Okay, and then we just keep in the back of our head, I is equal to the square root of -1. Right, it's just a thing. We know what it stands for. Okay, so we're going to treat it as a variable here. All right, so in this first example here, okay, we've got our binomial term, right, or our complex number here. Okay, and we're going to multiply it by 3. So obviously what we're going to do is we'll distribute the real number, right, our 3 here, we distribute it to both terms. So both of these get multiplied by 3. So 3 times 2 gives us 6, 3 times 5 gives us 15, right? And we just treat I here, again, like a variable, okay? Treat it like an X, okay? Since this doesn't have the same variable in here, you do not touch it, all right? If we've got 2 complex numbers here, okay? If we've got 2 complex numbers here, you're going to use the FOIL method, right? The FOIL method, okay? Now, the only special thing we need to remember here is that when we're dealing with I squared, it's going to equal -1, all right? I squared is going to equal -1, all right? And if you forgot why that is, all right, that would be because I have, all right, I have square root of -1, all right, and if I have equals I, sorry, so if I have the square root of -1 and I square that, it's like saying, obviously, square root of -1 multiplied by the square root of -1, okay? And in either case here, remember the square root and the to the power of 2, they undo each other, right? They undo each other here. All right, so regardless of however you see it, if it's in either of those forms, regardless, they're going to undo each other, right? So you're left with just a -1 there. All right, you're left with just a -1 there. So again, if I write it down here, I squared is equal to -1. All right, I squared is equal to -1. And I'll leave that there for a second while we go through this process here. All right, so again, if we see two complex numbers here, you just treat it like you would if we were dealing with polynomials here. You would just FOIL these out. All right, again, treating I like a variable, except it has a special property when it gets to this I squared here. So let's take a look. If we look at our first guy, 2 times 5, that gives us 10. All right, we look at our outer, that's 2 times 2i. Right, that's going to give us 4i. Again, 2 times 2 gives us 4. We don't touch the I variable. All right, inner, we've got -3i times 5. So that's going to give us -15i here. All right, and then our last term, we've got a -3i and a +2i. So again, 3 times 2 is going to give us 6, right, or -6 because it's -3 here. We're going to get a 6, and then we're going to have I times I, which is going to give us this I squared. All right, so obviously in the first step, leave it as I squared here. All right, then obviously the next step we would do is we would combine like terms. All right, so we would have 4i minus 15i. So that's going to give us a -9i. All right, a -9i. And then finally what we can do here is we can then replace I squared here with a -1. So this would be like saying -6 times -1. So this is going to get us a +6 value here. All right. So again, we collect our imaginary terms. Oh, wow. I did basic math wrong. I think I said that was supposed to be -9i. Wow. Apologies, y'all. But again, it happens to everybody. All right, so sorry about that. That's going to give us -11i. All right, and again, -6i squared. So then again, we use this I squared is equal to -1. So just like I said, right, it's going to have 6 times -1 or -6 times -1. We multiply those out, and we are left with our value here of 6. All right, and then okay, one final step here. Hopefully you notice I've got a real number at the beginning and a real number at the end. So what we're going to do is we're going to add those together. Okay, that's what it means by simplify. Right, so I've got 6 and 10, or 10 and 6. Okay, so that gives us our 16 minus our 11i. Okay, so we're left with 16 minus 11i when we're all said and done with this. Okay, so again, maybe a little bit confusing, but if you write it out step by step or line by line, right, it's going to be a lot more, a lot easier for you to keep it more simplified here. Okay. Now, jumping forward too, if we're dividing a complex number, okay, if we're going to divide a complex number by a real number here, okay, so first step is going to be write it as a fraction. All right, the first step is going to be write it as a fraction. The second step is going to be to split up the fraction, right, into 2 parts and then simplify. Okay, so what this is going to look like, if we convert our fraction, right, we're going to write our 6 plus I on top, or our numerator, and our denominator is going to be this divided by 2. Okay, so then when we split up our fraction, we're going to take 6 over 2, and we're going to have plus I over 2, right? That 2 gets distributed to both of those values on the numerator. Okay, then we simplify. Simplify if we can. So 6 divided by 2 gives us 3. All right, and then this is like saying 1 over 2. So I get a 1/2. All right, I get 1 over 2, 1/2 I. All right, so hopefully, again, not too terribly difficult. We write it as a fraction, you split up the fraction, and then you simplify. All right. Now, the next step here is going to be, what if we have to divide by a complex number? Okay, what if we have to divide by a complex number? All right. And this is where your weekend homework is going to come in handy. Hopefully you did it. Okay, again, because all right, because we're going to deal with the complex conjugates. Okay, so we're going to deal with the complex conjugates of our complex numbers here. All right. So just as if we had square root of x minus 1, okay, if with this one, right, we would have to multiply the numerator and denominator by this factor of square root of x plus 1. All right, so we're going to do the same thing here for our complex numbers. So if I have a plus bi in my denominator, I'm going to multiply the top and the bottom by its complex conjugate, which again is the same values, just a different sign between them. All right, so it would be a minus bi. All right, it would be a minus bi. All right, and again, if you want to see the math below as to why, okay, because if I have a plus bi multiplied by a minus bi, all right, when we simplify it all out, it ends up with a squared plus b squared. All right, and the reason that is because those middle terms cancel out, right? Our middle terms cancel out. And as we just found out, when I have I squared here, okay, that's going to say -1. All right, so I squared gives us a -1 value. Right, so I end up again with a squared plus b squared. All right, so if we want to look at a couple examples here, I can zoom in for us. All right, so looking at this first example, 1 plus I and its complex conjugate 1 minus I. All right, when I FOIL these guys out, again, the middle terms cancel. All right, because normally I would have a term here of -I and a positive I, right? And obviously those guys cancel each other out. So I'm left with 1 squared minus I squared. Well, we know that I squared is -1. So we replace that with -1. So I'm left with 1 plus 1 or 2. All right. If we look at our value down here for example 2, we've got 4 minus 3i and 4 plus 3i. All right. So again, same numbers, different sign between them. I'm left with 4 squared minus 3i squared. All right, and again, I can distribute that squared to both the real part and the imaginary. So again, it's 3 squared times by I squared, or 9 times by -1. All right, and then those negatives cancel out. So I'm left with 16 plus 9, which gives me 25 here. All right, it gives me 25. So again, it's much, much easier if we can get our denominator to be a real value. Okay, it's much easier if we can get our denominator to be a real value here. All right, so when we're dividing our complex numbers, okay, if we have a complex number in the denominator, we're going to have to use our complex conjugate to solve the problem. Okay, so again, the first step is going to be the same. Write the quotient as a fraction. All right. Now, this step is going to be a new one for this unit. All right. We're going to multiply our fraction by c over c. Okay. Again, where c is the complex conjugate of the denominator. So if you treat I like a real number, okay, this isn't much different than what we've already done. All right. But you're going to multiply the top and the bottom by this c over c. Okay, again, c is the complex conjugate, and the reason we can do that is because c over c gives us 1. All right, so it's effectively multiplying our equation by 1. All right, and then we're going to simplify the results using the processes that we know, because we want to end up with this form a plus or minus, right? Plus or minus our bi. So first step here, convert this to a fraction. All right, so we just bring what we're dividing by into our denominator. All right, now looking at this, obviously this is a complex number. Okay, so we need to multiply by its complex conjugate. And the conjugate for this one is going to be 2 minus I. All right, so I'm going to multiply the top and the bottom by 2 minus I. And the reason I can do this, because 2 minus I divided by 2 minus I, this is like saying multiplied by 1. right? It's like saying multiplied by 1. Okay, so when we multiply this out here, all right, if we start with our denominator, okay, if we start with our denominator, this is what we know, okay, so it's going to give us our 4. We're going to have a minus 2i plus a 2i. Those cancel out. Then we're left with a minus I squared. Okay, so before we simplify anything down further, that's what we're left with. Okay, for the top here, okay, we just treat this like 2 binomials. So we FOIL it out, right? That's the process that we went through. 4 times 2, 4 times negative I, 7i times 2, and 7i times negative I, right? That's all we did here. All right. Then if we start to simplify here, okay, obviously the top part to simplify, they just executed those normal operations, right? Like 4 times 2 gave us 8. All right. Now though, we're going to simplify even further because we can collect like terms, and for both the top and the bottom here, for the top and the bottom, we can turn this I squared into our value of -1. So take a look. All right, first off, we're going to add our like terms. Okay, then we're going to use I squared is equal to -1. So we replace that in 2 places here, all right, in our numerator and our denominator. Okay, then we're going to simplify down further. So I'm going to left with, hopefully you can see what they did there. All right, so I had 4 minus -1. All right, that's like saying 4 plus 1. So that gives me a 5 there. All right, then this was saying -7 times by -1. All right, this is going to give me a value of +7 here. All right, and again, this is a real number. So I find the other real number, which was 8. So I have 8 plus 7, which is how I got this 15 here. All right, which is how I got this 15 value. All right, so again, 8 plus 7 gave me 15. And now I've got this down into something that we're a little bit more comfortable with doing. Okay, now again, now that I've got it in this form and I've got a real number in my denominator, okay, I'm going to split up my fraction, right? So I'll have 15 over 5 plus 10i over 5. All right, plus the 10i over 5. And again, the reason it's plus here is because it was a plus 10i. All right, if this was minus 10i, this would be, again, minus 10i over 10. All right, but now that we've got it down into this, we can simplify both of these fractions. 15 divided by 5 gives us 3. 10 divided by 5 gives us 2. So we're left with 3 plus 2i. All right, 3 plus 2i. All right, and again, I know it took a lot of steps to get there. All right, but use up the lines on your paper or on your iPad or whatever, right? You've got plenty of space. All right, so I suggest you space it out like they did so that you don't get, again, lost with the negatives or the conversions or anything like that. Really take your time and try to write it all out, okay? So again, the steps for that was writing the quotient as a fraction, okay, multiplying by C over C, where C was our complex conjugate of our denominator. All right, then we simplified our results down until we got it into a fraction where we had a real number in our denominator. Once we did that, we split up our fraction into 2 parts, and then we simplified there. Okay, we simplified there. And one of the keys here, if you have to type in an answer, okay, if you have to like type in an answer for your quiz or for your test here, all right, you're going to have to write it in this form of A plus or minus BI. All right, so if you got to your final answer here, and it was one where you had to type it in, and you typed in 2i plus 3, right? You flip these, 2i plus 3. It might not give you the points for it, okay, because it's technically not in the correct form. So if you want to ensure that you're going to get all the points that you deserve here, you need to make sure you write it in this form, A plus BI, okay, A plus BI. All right, then to sum this little part up here, okay, multiplying and dividing by our complex numbers here. All right, adding, subtracting, multiplying, and dividing complex numbers is similar to operations with, I believe it should just be, I think the answer is fractions. Let me see here. What are they trying to get at? Oh, okay. All right. Awesome. So adding, subtracting, multiplying, dividing complex numbers is similar to operations with binomials. Okay. But I will argue with you, it is also similar to operations with fractions. It's also similar to operations with imaginary numbers and with real numbers. Okay. So I don't know why they asked this question the way that they did here. Okay. But regardless, what they're trying to get at here is that you can treat I like a variable. Okay, so that's what they're trying to get at with this statement here. All right, is that you treat I like a variable. Okay, and then you use the processes that we know to get rid of the variable or move it up or down or whatever. Okay, so again, treating our I like a variable, and then carrying out our processes the normal way there. All right. Again, complex conjugates, just to sum this up for us. Okay, complex conjugates are where I have A and B, and those are both real numbers. Okay, I'm left with a real part and an imaginary part, and then the complex version or the complex conjugate of it, all right, is having the same values but a different operation in the middle, right, or the opposite operation. So if I have A plus BI, its complex conjugate is going to be A minus BI. All right. And then to multiply or divide the complex numbers here, all right, I think they only gave us a couple steps, but we know that obviously there were more steps involved here. All right, if we looked at multiplying, okay, multiplying, we had to multiply the real number. So if it was just a real number, right? If we had our complex number multiplied by a real number, we just distributed that real part out, okay? If it was two complex numbers, we had to use our FOIL method, right? We had to use our FOIL method. And in this process, right, we had to turn I squared into -1. Okay, we turned I squared into -1. I'm sorry, yes. All right, I squared into -1. All right. When we were dividing, okay, we still wrote our quotient as a fraction. All right. And we had two processes here. All right. If it was already an integer, right? If we were dividing by a real number, right? A whole real number. Okay. It was easy. We just split up the fraction and solved from there. All right. If it was a complex number in our denominator, okay, we had to multiply by its complex conjugate in the form of C over C. We had to multiply by its complex conjugate, and then we had to carry out multiple processes until we got to this part here where it was just an integer on the bottom. All right, until we got to just this part where it was an integer on the bottom. All right, and then in both of these cases here, we simplified the result so that it was in this form A plus BI. It was in this form A plus or minus, right, BI. Again, being really careful that when you're writing these complex numbers, it is in this form A plus BI. All right, A plus BI. All right. Again, looking at some of these. All right, so this would be an example of just distributing out the real number to both parts. So you do 4 times 3, which gives you 12. Right, 4 times 3, which gives you 12. And then you would do 4 times 7, which gives you 28. All right, so you'd have 12 plus 28, and then you'd leave the I value alone. You treat it like a variable, so you've got plus 28I. All right. For this one here, a little bit more involved. Okay, so I'll let you guys try this one on your own. But remember, you're just going to use the FOIL method. All right, you're going to use the FOIL method. Once you FOILed it all out, you're going to be left with some kind of I squared value. Right, you change I squared into -1. Right, you change I squared into -1, and you go on from there. All right, so again, I'll let you try these on your own here. Okay, and then of course, same thing. All right, FOIL this guy out, combine like terms, simplify your I squared, and write it in this A plus or minus BI form. All right, same thing here. FOIL out, simplify. All right, For this one here, okay, write it as a fraction, and we're going to notice here, obviously we have a complex number in our denominator, so we need to multiply by its complex conjugate. Okay, so this one's going to have quite a number of steps here. All right, none of the steps are super difficult. All right, again, none of the steps are super difficult, so it shouldn't be intimidating to you that there are so many steps. It's just one more process, right? It's one more process. Same thing here. Okay, you're going to divide. You have to multiply by its complex conjugate. All right, multiply by its complex conjugate. And if you can do these problems, you can do the obviously easier integer problems. Okay, you can do the easier integer problems if you can do those. All right. Taking a look here at our study guide. All right. The keys here are going to be that, again, our imaginary unit I is defined as the square root of -1. Okay, so if you have the square root of -a, really you have I square root of a. Okay, you have I square root of a. Okay, so again, looking at these, you would simplify them down to I square root of a, I square root of a, and then if a can get simplified down further, like 25, right? If we can take the square root of it, you're going to obviously simplify that down further. All right, you're going to simplify that down further. Okay, and notice here, okay, that this is where it flips. So instead of having I square root of 25 or I5, right, if we can simplify this down here, we write it again in that form of 5I. Okay, where I goes after the integer. All right, again, after the integer. But remember, like we talked about with radicals in general, okay, if it's not under the radical symbol, we write it before. Okay, so again, being really, really careful with the order in which you write it. Okay, I goes before the radical, right? It's the same thing here. It's before the radical, all right? But it goes after the integer. So I square root of 7 versus 5I. All right, just being really careful with those guys. All right, and then this one, hopefully not too difficult, just separating out into the real and the imaginary. All right, and the two that I want to focus on here is 7I. All right, again, this is like saying 0 plus 7I, where 0 is our real part, okay? So we can still write this as a complex number. All right, it just has this 0 part as our real number. All right, same thing when we have just 15. 15 is our real part, but our imaginary number is the 0I. Okay, so again, everything is a complex number or can be written as a complex number. All right, so then obviously here to add or subtract, we just said we treat I like a variable. Okay, where again, we collect like terms, we add them together, and then we simplify. All right, collect like terms, subtract them, simplify. Okay. When we are multiplying, okay, we treat them like binomials, or again, still treating I like a variable. All right, so if we have our complex number just being multiplied by a real number, we just distribute that real number like we would normally. Okay, again, 3 gets multiplied by 2 and the 5, right? Not touching the I there. All right, if we have two complex numbers, we just FOIL them out. Right, we FOIL them out, and the only other thing we need to know for this is that we substitute in this -1 for I squared. All right, and once we substitute that in, again, we just simplify it down further, and we write our final product in this A minus BI form, or A plus BI form. All right, and then finally, again, to remind us to divide by complex numbers, we treat them like fractions. Okay, we treat them like fractions. All right, so you write the division as a fraction, and if you're dividing by a real number, it gets easy, right? You just split the fraction up into 2 parts, all right, and then you treat each part separately. So 6 divided by 3, 15 divided by 3, and then you write your final as your complex number in the A plus BI form. All right, if we're dividing by a complex number, we still write it as a fraction, but again, we add in this extra step here where we multiply by a fraction where it is the complex conjugate. All right, And I want to point out here that they messed up, so don't let it confuse you. Okay, this should be 6 plus 2i on top as well. Okay, so they did mess up here in the answer key, so don't let that confuse you. Okay, this has to be the same, otherwise it's not multiplying by a value of 1 here. All right, so there should be a 2 right here in front of this 6. There should be a 2, or sorry, in front of this I. All right, so it should be 6 plus 2i over 6 plus 2i. All right, so don't let that confuse you. It's even there if you see it, right, when they did the FOIL. It's right there. All right, but again, once we have FOILed this out, we replace our I squared with a -1. We are then able to get a real integer on bottom. Okay, then we follow the exact same steps we did up here. You split it into 2 parts, and then you simplify. Okay, so hopefully it's not too terribly difficult here. All right, and when we look at our checkup, I can bet you it's going to be a lot of practice problems here. All right, so first off, adding and subtracting. Okay, again, this is just basic collecting like terms, making sure you're keeping your signs straight. All right, doing the products here. All right, again, this is going to be using your FOIL method. Still just replacing that square root, or that I squared, with a -1 when you get to that point. And then obviously finding the quotients. All right, and all three of these are going to require you to multiply by the complex conjugate. Okay, because again, if you can solve this one, you can solve basic integer problems as well. All right, same thing up here. If you can solve these guys, you can solve multiplying just 1 by a real number. Okay, so again, I suggest you work a little bit on that before you take your quizzes here. All right, and again, I want to point out your quizzes are separated by a pretty good divider here, right? This first one is only about adding and subtracting complex numbers. All right, so if you feel confident with this one, but maybe you're a little bit shaky on multiplying and dividing, right? Well, that's great. There's 2 separate quizzes for that. Okay, so you can always split those guys up here. All right, so you've got 2 quizzes, both of them are mandatory. All right, you've got 2 quizzes, both of them are mandatory here. Okay, so that's the first thing you've got to do tonight. All right, 2.9, moving on here. All right, 2.9. All right, we're not going to spend a ton of time on this one because, again, like I said, this performance task here, this project, do not even attempt it. All right, it is pretty lengthy here. If you look, it's 120 points. All right, and if we were to look at how many pages it is quite a number of pages. All right, I think it's like 10 pages if you were to send this to Notability. All right, so not super worth it here. Okay. Obviously, it won't be asked of you on your test either, all right? But again, this would be something more like a STEM project here, okay? But if we were to just gloss over this here so you guys can see it, we're going to deal with this thing called a skid distance problem, all right? So again, I believe it was introduced earlier in the unit, but this is talking about cars. So obviously when you slam on your brakes and those black marks, those are called skid marks, okay? Those are called skid marks in the road, right? And it's obviously indicative or represents the fact that someone slammed on their brakes but continued to go on the road, okay? And this kind of problem here is how when you take driver's ed, right, they're going to tell you something along the lines of, when you're driving on the road, you should have at least X amount of distance between you and the car in front of you, right? And I was always told, you know, some general number like 3 car distances or 3 car lengths between you and the next car, right? I don't know what they'll tell you now, but that's what I was told when I was growing up, okay? And how they came up with that is something along this lines of, okay, well, how far is a car going to skid if you slam on your brakes, and is it enough stopping distance so you don't hit the person in front of you, right? And we can watch the rest of this here, but that's essentially what they're going to try to ask you.
Police officer arrives at the scene of an accident where one car has clearly hit the back of another car. The car that caused the damage left skid marks on the asphalt road before hitting the car in front of it. These skid marks measure 97 feet in length. By looking at the amount of damage to the two cars, the officer is able to calculate that the car was going 35 miles per hour when it hit the other car. But the officer must now figure out if the driver of the back car was going more than the speed limit of 50 miles per hour before starting to skid. In other words, did this driver break the law?
Okay, awesome, right? So looking at those kinds of things. All right. So again, if we were to do this, we would have dissected, all right, all these different questions, right? So how far did the car travel once the brakes were applied? What was the speed going before the brakes, right? And looking at all those different factors. So what he said was it was a 97 foot long skid, right? And he knew that he was going, I think they said 35 miles per hour when he hit the car. So then we would have to back calculate how fast was he going before he started to skid along that 97 foot length. All right. So then what we would have dissected here is looking at, well, how good are the brakes? All right. So you could call it this thing called brake efficiency. All right. So how good are the brakes? All right. And each brakes are going to be different, right? And as you drive your car, your brakes might wear out, and you might hear your parents talking about this, right? Or something along the lines of, my parents always said, like, oh, the brakes are spongy. All right. Meaning you have to press down a little bit harder because the brakes weren't working as good. All right. So we could look into that factor, right? And if again, if this was a STEM project here, right, maybe groups would have different brake efficiencies, right? Maybe you might be dealing with someone whose brakes are perfect or whose brakes are maybe at half efficiency, okay, looking at how that changes a problem. All right, we could have also looked at this thing called drag factor. All right, so again, you'll learn more about this in physics here, but it's a measure of friction between the tires and the vehicle, or sorry, the tires of the vehicle and the roads on the surface. All right. So when you're dealing with something like air hockey or normal like ice hockey, okay, the reason that a puck can move so far when you only tap it a little bit, right? Hopefully everybody's watched hockey or played air hockey at some point, right? You touch it barely and it moves for what seems like a really long time, okay? The reason that is because it has no drag, all right? So we could look at, again, how much friction is there on the road. All right. So again, we could look at a lot of different things. So again, road surfaces, if we were to put these in order of longest stopping distance to shorting stopping distance. All right. So the longest one would be something like ice, right? Again, if it's like driving on ice, that's why they say when it's snowing or when there's ice out, you need to be really, really careful. Okay. So snow and ice would be take a long time for you to slow down on. Then I believe concrete would be the next one, right? That's the next smoothest road. Okay, then you've got asphalt, right? Which is like that gravelly rock, but it's still all padded down. So that one gives you a little bit more drag or friction or, you know, resistance. All of those are kind of meaning the same thing. And then gravel, right? That's just a lot of different rocks and distances here. Okay. So, oh, and I put these in the opposite order. So if the longest stopping distance here should look like, I believe, like this. Okay. So they're saying that that, okay, they're saying that since gravel is loose, it's dangerous, which, sure, you know what, they did the test, they figured it out, right? And what we would have done, or what we could have done, right, is we could have had, hopefully you've seen them if you were ever in Mr. Diaz's room, all right, but you could have seen those little toy cars, right? So we could have actually taken toy cars out and measured how long it takes for them to stop, right? On these different surfaces. We could have figured out these things called drag factors. But again, how this relates to you is knowing that different environments that you're driving on are gonna cause your car to react differently. So again, we could have looked at those moving forward. All right, so then again, looking at these average drag factors, if we were making this into a STEM project, each person could have had their own road surface, right? You could have looked at your own road surface, what happens as you have different amounts of brakes, all right? So then obviously the last thing we needed to look at was speed before braking, all right? So if we were to look at all of these different speeds here, okay? So the different speeds end up with different skid distances, okay? So it ends up making this kind of relationship here. If I was at 70 miles per hour, I was gonna have a skid distance of 181. Versus if I was only going 10 miles an hour, I would only have a 3.7 foot skid distance. All right, so speed obviously plays a role there. Okay, so then we could have gotten this relationship here. Okay, and then we could have made our equation. Right, we could have made an equation based on relationships that we know. Right, we could have made an equation here. All right, and then we could have plotted all of our different factors. All right, looking at our different factors, and we could have eventually solved for our speed here. All right, we could have solved for our speed, looking at our skid distance equation that we generated, okay, substituting in our mark length for our distance. All right, simplifying and then calculating our speed there, okay? And then obviously restating the question, okay? So that would be one example there, okay, of solving for our speed, okay? And obviously, like I said, I don't want to spend too long on this, but that's something that we could have really taken some time and dissected all these real world practical applications here. Okay, so by all means, you are welcome to take a look at this study on your own, but this project here is not mandatory. So it is not mandatory. You do not have to do it. All right, not mandatory. Do not have to do it. All right, so far you have 2.8. You have these two quizzes here. All right, you have these two quizzes. 2.9, by all means, you are welcome to look at it, but there is nothing for you to do, not even extra credit opportunity. Okay. Then finally here in 2.10, all right, 2.10, I want to spend a couple minutes going over this, this checkup and this review here, all right? So if we look at, let's do the review here first. Okay, this entire unit was on radical expressions and functions, and I know there was a lot of different things that we talked about here. So again, taking a minute to review is going to be really helpful, all right? So we had some basics of radicals. All right, so what are the properties of radicals and what are their products here? Okay, so if we look at this one, all right, talking about how do we do and undo radicals. All right, so if I have the square root of something and I square it, okay, if I have the square root and I square it, that undoes the radical. Okay, that undoes the radical, all right? It will undo the radical, and it doesn't matter if you square root it first and then take the square, or squared first, then you take the square root, right? It's gonna give you the same answer, all right? Then for any non-negative numbers, okay, so we can multiply our radicals together, and as long as they have that same index value, right, so this is square root multiplied by square root, you can combine them underneath the same radical symbol, right? And again, that was really helpful for us when we had smaller numbers for A and B. When we were able to multiply them out, we could simplify them. All right, and then obviously we had a similar property for the quotient, right? If I have, again, the same index number, so this is a 2 and a 2, okay, if I have a square root divided by a square root, I can combine them under one radical symbol. All right, so again, those were really, really helpful for us. Okay, then when we were multiplying and dividing radicals, okay, we had a couple rules for multiplying and dividing them. So first off, notation of radical expressions. All right, and we just re-highlighted that. But for our radical, okay, if it's multiplied by a variable, that should be put in front of the radical, right? So again, we said putting the number in front of the radical. So 2 radical x, x radical 3 plus x, okay? Because again, if this 2 is in the back here, it's really confusing to know if it's underneath the radical symbol or not. All right, so we write our values that aren't under the radical symbol out in front. All right, then when we're looking here, what are the product properties for radicals that contain variables? All right, so it's the same thing here. All right, so if A is a variable, okay, it's going to follow the same properties. Okay, squaring a square root undoes that value. Okay, squaring a square root undoes that value. All right, and it'll follow the same principles here for multiplication and division. You can combine them under the same symbol as long as they are both the same radical. Okay, same thing for the division property. All right, it's going to be able to be combined as long as it is, again, the same radical form. Okay, when radicals have like terms, okay, when radicals have like terms, you can combine them. All right, and they are like terms if they have the same degree and the same radicand, right? So again, if I have an x squared term in there, okay, I have to have an x squared term somewhere else. All right, and they have to have the same radicand. So an example of 2 that might be similar here, if I write them out, so it might be x, let's go with x square root of 5, all right, and 3x square root of 5. All right, those are similar. Okay, those are similar. All right, but what's not going to be similar is if I have x square root of 5 and 3 square root of 5. All right, and the reason that is because it fails this first one. They don't have the same degree, right? This is x to the first power. This is just a constant, or x to the 0th power. All right, so this is an example of where they're not similar. Okay. All right, and then adding and subtracting the radical expressions. Okay, so when we add and subtract them, okay, we just need to combine like terms. All right, so again, if I have a radical 5, I can add them together, right? I don't add the radical 5 plus radical 5. We treat that like it's a variable. All right, we treat that like it's a variable. Okay, rationalizing the denominator. We spent a lot of time with that in today's lesson. So again, but it's multiplying by its conjugate. Okay, multiplying by its conjugate. All right. And then the steps for solving a radical function or equation here is obviously isolate the radical, square both sides, and then solve for the variable using whatever operations and methods in order to get the radical or the variable by itself. Okay. And something, again, important with this one here is always making sure you check your answers, right? We had a lot of, or the lecture this weekend talked a lot about if you have something that looks like a quadratic, right? You might have those things called extraneous roots, right? You might have extraneous roots. So knowing to go back and check those. Okay. For again, applying radical functions. All right, this was talking about those real world problems. Okay, so when you have a real world problem, the steps are as follows. Identify the formula or function that you're going to use, right? Figure out what you have and what you can use. Identify the known variables. Again, what do you have? substitute in, isolate the variable, and then state the answer. Okay, so again, the biggest part I think with this application problem is number 1 and number 2. All right, isolating the formula and isolating or identifying your known variables. Those are going to be the biggest things here. All right. And then finally, nth root. Okay, our nth root. That's talking about things other than just our square root here. Okay, so we can have our n here be any positive value. All right, and that's called an index. Okay, our index of our radical. So when we have a square root here, our index is 2. Or if I have the cube root, our index is 3. All right, and what we found is that we can also write this in exponential form. So we can write this as 1 over n, right? Where again, n is our index. Okay, then we can figure out if the values are real, right? So again, this is where if our index was odd, we can have a positive or negative radicand. It doesn't matter, right? It's only when our index is even and negative do we run into these problems, right? And as we found out, this is because we're going to use that imaginary number I here. All right, so if we have an even and a negative, we're going to have to use the imaginary number I. All right, so then expounding upon our rational exponent here, okay, we could take it from just being 1 over n to being this phrase m over n, okay, where we take our value, we raise it to the nth power, and we take the nth root of it. All right, and what this is showing you here is you can do the to the power of m first, then take the root of it, or you can take the root of it and take it to the nth power. All right, they're both going to end up with the same thing here. All right, so then finally here, how did we write a decimal exponent as a rational exponent? Okay, what we could do is use the properties that we know for exponents, all right, and we can write the decimal as the sum of rational numbers, all right? We write it as the sum of rational numbers. So if I had 5.25, right, I could write it as 5 plus 1/4, 1 over 4, right? Then I can split up the product using that multiplication property, and I can reduce each of the individual fractions here. All right, and then obviously the last one here was complex numbers that we just went over today. All right, taking 30 seconds to look at the checkup here. All right, again, it's going to go through and do a little bit of problems from each of the units. So I really highly suggest that you go through and look at these problems here, because if you get stuck on something, let's say you get stuck on, I know we just talked about this, but let's say 17 through 20. Okay, you can look at and figure out, oh, okay, well, this is from the last unit on complex numbers. You can go back and then look at that. Right? Or if you get stuck here on this first part, obviously that's going to be in one of the earlier units here. Okay, and you can use our review here to figure out what units that's going to be in. Okay, and then obviously you have your CST, and that's the last thing you have to do today. Okay, so 2.8 we covered in class. You have 2 quizzes for that, so go and take those. 2.9 you can review on your own if you'd like, but there's nothing you need to complete for me. And then you're taking your unit 2 test here. So you're going to take this 2.10.3 CST only. Okay, and this should be open for everybody. If for whatever reason it's not open for you, please let me know immediately. Okay, so again, that's going to conclude today, and we're going to end about 19 minutes early because I know that tests take you a little bit longer. So here's an extra about 20 minutes that you can get started on either your quizzes or on your test here. Okay, so tomorrow we'll start unit 3. And if you have any issues tonight, please email me immediately and I'll unlock whatever needs to be unlocked. Okay.